This is lesson 10, practice problem number 1. And in this problem, you are given 3 lines and 3 slopes. A slope of 1, a slope of 2, and a slope of 1/5, and asked to match these 3 slopes with these 3 lines. So this is practice in identifying what this slope means. And so the larger the number, the larger the slope, the steeper the line. So the very steepest line is going to have a slope of 2. We're going to talk about what that 2 means in a moment. The next steepest line has a slope of 1. And the least steep line, the one with the smallest slope, has a slope of 1/5. So you can match them just based on that. This is the yellow line is the steepest, so that's a slope of 2. Blue line is the next one, slope of 1. And the black line is the least steep slope, the smallest slope, so that's a slope of 1/5. The vertical length gets longer compared to the horizontal length as the slope increases. So as the slope increases, as it goes from 1/5 to 1 to 2, this vertical length, this direction, is getting longer compared to the horizontal length. So the vertical length gets longer compared to the horizontal length as the slope increases. So to look at these, I drew a single vertical line at x equals 5. So if this is x equals 0, 0, this is 1, 2, 3, x equals 0, actually. 1, 2, 3, 4, 5. So this is where x equals 5. And so now we can look at just the vertical length for each of these and compare them. The horizontal length is the same. And I also drew these slope triangles. It's very useful to draw slope triangles at this stage to help you understand. So keep drawing them until you just don't need them anymore. Okay, let's look at the first one. This is the slope triangle for the blue line, and it has a slope of 1. It has a vertical length of 5 units, a horizontal length of 5 units. So along the x-axis, it goes 5 units. Along the y-axis, it goes 5 units. So the slope is how the vertical length compares to the horizontal length, or how much the vertical length is changing compared to the horizontal length. And it's 1 for 1. So if you go over an x value of 1 unit, the y value is 1 unit. X value 2 units, the y length is 2 units. The x length, or the horizontal length, is 3 units. The vertical length is 3 units. So it's the vertical length compared to the horizontal length. In this case, that relationship is 1. Vertical length is 1 unit. The horizontal length is 1 unit. I compare that to the black triangle, in which the vertical length is 1 unit, for the horizontal length being 5 units. So this is a much shallower slope, or a less steep slope. It's just not as big. So it goes over, the horizontal length goes over 5 units, but the vertical length only goes up 1 unit. So it's not rising very much compared to the horizontal length. So if you go down here, this is 1 unit along the x-axis, or the horizontal length. What's this value right here? It is 1/5 of a unit. It's 1/5 of a square. Well, if that's true, what's this one? Well, that's 2/5. So it's only rising at 1/5 for each horizontal length. So this is 2 lengths along the horizontal axis, or the x-axis. This is 2/5. 3, this has a length of 3 units, 3/5. Has a length of 4 units, 4/5. And has a length of 5 units, 5/5, or 1. So not increasing very fast, a small slope, a slope of 1/5. So how much is the vertical length changing compared to the horizontal length? It's 1 for every 5 units horizontal length. Not very big. Whereas the yellow triangle has the largest slope. So it is going up 2 units for every 1 unit in the horizontal length. So it goes 5 units out, goes 10 units up. So this is going up faster than the blue triangle. It's going up much faster than the well, let's call it blue line, much faster than the black line. So if you look at 1 unit, if you look at 1 unit, if you go in the horizontal direction 1 unit, so this is the length of 1, what's the vertical length? Well, that's 2. It goes up twice as far. So horizontal length or along the x-axis 2 units, this is 4. 3 units, this is going to be what? Well, it's going to be twice as fast or twice as far. It's going to be 6. 4 units, this is going to be 8 units. And 5 units, this is going to be 10 units. So it's rising the fastest compared to the length in the horizontal direction. So the vertical length compared to the horizontal length is 10 to 5 or 2 to 1. So this has a slope of 2. It is rising the fastest compared to the horizontal length. Problem number 1. This is lesson 10, practice problem number 2. And so for this problem, you're supposed to draw 3 lines, 3 different lines with a slope of 2 and 3 different lines with a slope of 1/3. So for the slope of 2, and actually for the slope of 1/3, I drew the line plus the slope triangle. It just helps me see what's going on. So this has a slope of 2. So if I have a horizontal direction of 1 unit, I'm going to have a vertical direction of 2 units. So a slope of 2 means that the y length, the y value is twice as large as the x value. So you have an x length of 2 units here, the y length is going to be 4 units. So for every unit along the x direction, the horizontal direction, the vertical length is going to be 2 units. So down here, if the horizontal length is 3, then the vertical length has to be 6. 1, 2, 3, 4, 5, 6. And if the horizontal length is 4, the vertical length has to be 8. Then I extended those lines out. So these are the lines, and then I just included the slope triangles. I did the same thing for a slope of 1/3. And so again, if you have a horizontal length of 3 units, then the vertical length is going to be 1 unit. 1/3 of 3 is 1. And so if you have, another way of saying that is that the horizontal length is going to be 3 times as long as the vertical length. So over here, it might be easier to look at this vertical length as being 3 units. So this horizontal length is going to be 3 times as long, or 9 units, or the other way, if the horizontal length is 9 units, the vertical length is going to be 1/3 of 9, or 3 units. 1, 2, 3. And this last one is this triangle way down here. It's just 1 unit. So this has a horizontal length of 1 unit. So what's the vertical length? It is just 1/3. It's 1/3 the length of along the x direction or the horizontal direction. The other way of saying that is if you have a vertical length of 1/3, then the horizontal length has to be 3 times that. 3 times 1/3 is 1. It's going to be 1 unit. Now what I did is I shaded in the slope triangles with a horizontal length of 1 unit for each one of these. So you might call this the unit horizontal or the unit slope triangle. So an x value of 1 unit. What's the y value in each case? Well, it's going to be 2, 2, and 2 for a slope of 2. Or a horizontal length of 1 unit, it's going to be 1/3, 1/3, 1/3 for a slope of 1/3. So what do you notice when you look at all of these together? Well, the slope of 2, you have 3 lines, 3 separate lines. Those lines are all parallel because they all have the same slope. It makes them parallel. So it's moving up in the vertical direction at the same as the horizontal direction for each of the 3 lines, and that's 2 to 1. And the slope of 1/3, you have 3 separate lines. Those lines again are all parallel because they all have the same slope of 1/3. So they're moving up 1/3 of a unit for each unit along the horizontal direction. So a slope of 1/3. We'll get a little bit closer. If you look at one pair, look at this unit length and then compare how fast or how far it's going up in the y direction for each one of these. A slope of 2, this is a much larger length than a slope of 1/3. This is only 1/3 of a unit, whereas this is 2 units in the vertical direction, or the y along the y-axis, compared to a single unit in the x direction. So another pair, they're all going to be the same because they are all the same. So this is just a separate pair. The x value is 1 unit, but notice the y value. It's 2 units, and in the slope of 1/3, it's just 1/3 of a unit. So this is a small slope, very small slope, and this is a steep slope compared to each other. And so this has a slope of 2, so it's going up these 2 units compared to this just a single unit along the x-axis, or the horizontal length. Horizontal length of 1 unit, vertical length of 1/3 of a unit. So if you look at them all together, once again, if you have a slope of 2, each of those lines are parallel. If you have a slope of 1/3, each of those lines are parallel because they have the same slope. And you should be able to find what I called this unit slope triangle. For a single value of x equals 1, you should be able to find those in each line, and they should be congruent. Each of them should be the same for the same slope. So this is lesson 10, problem number 2. 3 different lines with the same slope for each one of those. This is practice problem 3 for lesson 10. And in this problem, you're supposed to figure out the length of xy. So what's this length right here? You can actually just count the squares. But how do you mathematically figure out that length? What's the slope of this line? So you're going to calculate the vertical length compared to the horizontal length. So 2 divided by 4, and so that slope just kind of falls out from that calculation. And first of all, actually, you're supposed to go through an argument of why this triangle, this slope triangle right here, is similar to this slope triangle. Well, xy is 6 units long, and as I said, you can just count them. But also, you look at this long enough, you start to realize the vertical length is half the horizontal length, or the horizontal length is twice the length of the vertical length. So this has a slope of 2 divided by 4, or 1/2. So for every unit that you travel along the x-axis, you go up a half of unit. So this is a half of a unit. So if this is 2 units, the vertical length is 1 unit. So it's 1 to 2, or 1/2. 4 units, the vertical length is 2 units. And this one, the horizontal length is twice the length of the vertical length on the y-axis. So if this is 3 units, this has to be 6 units. All right, so let's go through an argument of why these 2 triangles are similar. These are 2 slope triangles on the same line. We, in essence, just got done doing this. We looked at the same or similar slope triangles on different lines and found that those lines are parallel, so they have the same slope. Well, now those slope triangles are just on the same line, and so they have to also be similar triangles. So one way to show that is to show that 2 of the angles are congruent. Well, you know that this angle right here is 90 degrees. And that means that you just have to find one other angle that's congruent. So you can just translate this whole triangle up here, and shows you that this angle falls right over this angle here of the larger triangle. So this angle is congruent. This angle is congruent with this angle. So these 2 triangles are similar. And remember that these are all 90-degree angles. So these triangles are similar. These 2 triangles, the pink triangles, are actually congruent. They're the same triangles. Right, that's one way to show that, through a rigid transformation, in this case a translation. The angles don't change size, they just move within this coordinate grid. And if you can cover another angle exactly, then those 2 angles are congruent, and those 2 triangles then are similar in this case. right, you can use this idea of parallel lines also. How can you move this angle to this angle up here? Well, you can do that through a rotation, a 180-degree rotation. Remember, this angle is going to rotate around because these two lines are parallel. The midpoint, this is the center of rotation. The midpoint's right here. This angle is going to rotate 180 degrees and land right here. So this angle is congruent to this angle. It's just gone through a rigid transformation of a 180-degree rotation to go right to here. So this angle is still the same. It's just rotated. And then remember that this angle across this intersection is a vertical angle. It is identical. So this angle is identical or congruent to this angle. So we have in fact moved this angle here up to here and shown that they're congruent. So now once again you have two angles within similar triangles that are congruent. That makes those two triangles similar. So that means that you can use that information to figure out the length of x, y. Because they're similar triangles, they have the same slope, so they're going up compared to going across. So the slope is the vertical length compared to the horizontal length. So how fast or how far is it moving up the y-axis compared to how far it's moving along the x-axis? How fast is the line rising? So we know from this similar triangle here that that is 1/2. So it goes up, the vertical length is 1/2 the horizontal length. So if this length is 2 units, the horizontal length is 4 units. So that is a ratio of 1 to 2, or 1/2. You can use that information. So it's going up 1 unit for every 2 units in the horizontal direction. And you can use that information to figure out what x, y is right here. So this is 3 units in the vertical direction compared to whatever the length is in the horizontal direction. So it's 3 compared to h, the horizontal direction. We know that that relationship is 1/2. So an equivalent ratio to get to 3, you multiply by 3 over 3. So 3 times 1 is 3. And 3 times 2 is 6. So this is an equivalent ratio to 1/2. And that makes the length of x, y 6 units. So you're using similar triangles, in this case slope triangles, to figure out unknown lengths by using that relationship called the slope. Problem number 3, lesson 10. This is lesson 10, problem number 4. So you're given two triangles, triangle A, which has side lengths 3, 4, and 5. And I drew this in Docere, and I made these lengths approximately 3 units long, 4 units long, and 5 units long. And then triangle B that has side lengths 6, 7, and 8. Well, I drew a similar triangle to A, and I called it B prime. It's actually not triangle B, so I just called it B prime. And this similar triangle has a scale factor of 2. So 2 times 3 is 6, so this length is 6 units. 2 times 4 is 8, so this length right here, the corresponding length, is 8 units. And 2 times 5 is 10. So this corresponding length is 10 units. The point is that you can't draw a similar triangle that has lengths 6, 7, and 8. You can go from 3 to 6, so you can use the 6. So 2 times 3 is 6. You can go from 4 to 8, so you can use the 8. 2 times 4 is 8. But then when you get to the 5 unit length side, you multiply that by 2, you get 10. Not 7, but you get 10. So the point is there's no single factor, the same factor that you can multiply by to move the lengths of A to the lengths of B. So no, you cannot draw similar triangles. Now, I did part B, just in how I set it up, give possible side lengths for triangle B so that it is similar. Well, you just change, instead of 7 units, you change this length to 10 units, so this triangle is scaled up by a factor of 2. There are other triangles you could draw, or at least one other triangle you could draw, but we'll use that one right now. So this is a scale factor of 2. So 2 times 5 is 10. So this is problem number 4, practice problem number 4, lesson 10.